All right, so here's where we were last time. We were talking about how to use coordinate conversion formulas as change of variables functions. Right? It was a little bit of an odd idea, but hey, it fits, right? I mean, they do what they need to do, and when you do so, you can compute certain integrals, like this integral defined on this domain right here. This is an ugly integral. If you try to do that in the usual, in rectangular coordinates, you get some nasty antiderivative issues that come up. So what we found, first, you can view that as an image without too much trouble, a little bit of trouble, but you can view that as an image, and thereby, with change of variables, you could pull back to an integral on this much nicer domain over here, much friendly. All the algebra works out way better once you do that pullback. So that's the first observation. And then the next observation is to realize, even though, yes, we're going to do that, we don't even actually have to geometrically draw it or even particularly visualize it in those terms. We can see anything that I would need to do over here. For example, theta slicing. I can see all of that right here in the XY plane. So I don't even really have to realize that I'm doing that, right? In some sense. I think it's, of course, always healthy to understand what you're doing, right, intellectually. So anyway, this is the picture that remains of what we mean when we say we're doing an integral in polar coordinates. The range of values of theta you identify by looking at these theta slices and seeing that you have this lower bound comes from that theta slice, and then this theta slice here gives you the upper bound, etc. Okay. All right. And then I left y'all with some tips and tricks that I think are useful, in particular, for all practical purposes. Just always use this order for the differentials. It's not even worth talking about going the other way. So easy to forget the stretching factor. Oh my gosh, so easy. And tragic. It costs lots of points because that stretching factor, that silly little factor of R, right, is the big multivariable calculus concept in play here. That's the thing that's the only part of this that isn't just kind of plugging in some sense. So it's a very, very important, very easy mistake to make, and therefore, I think, very worthy of having a memory tool, memory trick. And so mine is, I don't ever write down drd theta by itself. If I can help myself, right? I have every intention of never writing down drd theta by itself. Why would I? Anytime I write down drd theta, there's going to be an R that has to be attached to it. Why wouldn't I just write it down at the same time? So I urge you to do the same. And then again, our process, ultimately our process for finding the bounds in polar coordinates, just like with rectangular coordinates. You identify the key points, recognize them as being on certain curves that have certain equations, and then solve for what you need. Okay, so moving on. Another example. Let's consider this integral defined on an annulus, which is this kind of a ring-like thing here. All right, so how would we do an integral on this annulus? There's a couple ideas that you might consider. One would be to say, oh, hey, clever, how about this? How about I first view this as an integral defined on this purple region. Let's compute that purple region first, and then I will subtract that from the integral on this dark blue region. And dark blue minus purple should give me the light blue, shouldn't it? One would think. It's very tempting. Here's the big problem. This integrand has a discontinuity But how? Right? It has a massive explosive discontinuity at the origin, which means that neither one of these integrals is defined. So you can't do that. That's just not a thing. Right? And you may be thinking to yourselves, well, can't we use improper integrals? That's a much more complicated story in multivariable than it is in single variable, and we're not going to get into that. And roughly speaking, it's not. You don't want to go that way. Okay, so we can't do that. So what else are our options? By the way, notice the failure. Notice the discontinuity in this point doesn't affect the integral at hand, right? I mean, what we're actually interested in, the integral over this blue region, no problem. This integrand has 0 issues on the blue region, right? Okay. All right, so what are we going to do? Seriously, next option, if we were going to do this in rectangular coordinates, we would have 1, 2, 3, 4 separate regions to break it up into, whichever way you slice. And nobody wants that. This is a pretty undesirable option as well. So this is just a tailor-made perfect example for using polar coordinates. It's lovely. Our scary integrand that we had rewrites like that in polar coordinates. Nice and easy in polar coordinates. Our differentials, don't forget your stretching factor of r. Dx dy, in other words, turns into r dr d theta. The bounds here are pretty straightforward. Theta goes from 0 to 2 pi. Then for any given value of theta, for any given theta slice, let's see here, theta slice, right there, right? We can just look at the specifics of our annulus. This point that represents our starting value of r, that point is on this curve, which has this equation, in which I can solve for the variable that I'm interested in here. Again, I'm looking for an r bound, so I need to solve for r in this equation. Oh good, it's already solved for. Isn't that nice? And so there's your lower bound, right? And then likewise, let's see here, the ending value, let's see, is going to be at that point, which is on that curve, which has that equation. Again, easy to solve for r. There. So in polar coordinates, nothing to it. And not only is it easy to set up, it's actually, in this case, even easy to integrate. Look how easy this integral is. Our integrand is a constant. All right. That's wonderful. Very convenient. Okay. All right. Next example. This one's a little bit less sort of immediate, a little bit more trickery that's involved here. I like this example for that reason. So here's our integral in question. Our domain is described by all this jazz up here, and don't get lost in the notation. All this means is, if you just kind of break it up into pieces, this says I want points whose distance from 1, 0 to be less than 1. So that's this disk, right? And then this business here says I'm excluding, well, now again, keep in mind that's what this red slash means. That means not including, right? So we're going to exclude what we have in orange, and this is just the unit disk. So I'm looking here, my domain here is that I'm momentarily going to color in green, is the yellow disk, the part of the yellow disk that does not include the orange disk. And so, of course, that's just this right here. There we go. Does everybody see that? All right, so there's our domain. What are we going to do about this? Well, let's, for one thing, RD theta. Again, don't forget to always include the R as you're writing down the differentials. It's a really handy little memory tool. It'll save you from accidentally stepping on a landmine. And you'll never know what landmines you might have stepped on because you won't have stepped on them if you follow this rule. Okay. X, of course, easy to write in polar coordinates. Nothing to it. X is just r cosine theta. And then let's see here. Now we're into the slicing. What's the range of values of theta? Here's a little bit of a tricky bit here. Now there is another more algebraic approach, but look for the beautiful opportunities. This lower bound of theta, by the way, let's draw our theta slices. Our theta slices all look kind of like this. Right, these are all rays emanating out of the origin, representing different values of theta. So our lowest value of theta comes at this point. And what can I say about that point? Here's the trick. Notice that this and this are radii of this circle, which I know has radius 1. And then notice that, let's see here, color choices. This is a radius of this circle, which I also know has radius 1. And so, different geometric observations there, but altogether, that tells me that this is an equilateral triangle, and I know all the angles in equilateral triangles. That's freebie, and so therefore, the angle that I'm interested in here, this starting value of theta, is just, well, it's negative pi over 3. Everybody follow that? That was some clever little using the given algebra to infer some geometry and avoid a little effort. Okay, and then likewise for the upper bound, analogous argument, this is an equilateral triangle here, therefore positive pi over 3. Make sure you can think it through. Persuade yourself that this is indeed an equilateral triangle. Right? Think through the details. Okay, then for a given value of theta, fixing theta now. Where does R start? Where does R end? Well, R starts at that point, which is on that curve, which has that equation, which puts my starting value of R as 1. My ending value of R, that point, which is on this curve, where we have to kind of do some thinking here, don't we? That curve, I can write down arguably the rectangular equation relatively easily, but I need to solve for R. I'm looking for an R bound, right? So I don't see the R in here. So I've got to then convert that equation into polar coordinates. Flashback to chapter 1, right? How to convert equations. And once you have it in polar coordinates, well then solve for R, and there's your upper bound for R. Is everybody happy with that? Okay. All right. Now, their case could be made that this integral right here doesn't look particularly nice, and I'm arguably a little scared of what's going to happen when I do this R integral. I'm going to get an R squared, which, oh no, wait a second, I'm going to get an R cubed because I have an R squared already, and that's going to give me a lot of factors of cosine in there. But remember, when you're doing trig, you have trig identities to work with, and this is really nice. The alternative, I remind you, still on the table, I suppose, you could do this in rectangular coordinates. But the problem is that in rectangular coordinates, you're going to have to chop this up into 3 pieces. And worse, each of those 3 pieces will have edges of circles involved, which means you're going to have square roots all over the place. And I consider that to be quite a bit worse. So, if you don't believe me, try it both ways. I think you'll like this one better. Okay. All right. So, this next example, I'm going to skip. This is a luxury that I like to be able to go through when we have time. And of course, as y'all have noticed on the lecture schedule, we're pretty behind at this point. So I don't have time to talk about this one. But this is a nice little bit of math culture also, because it's a really important calculation. The value of this integral is pretty significant in study of statistics, as it turns out. So it's a kind of a big deal. But computing it from a single variable calculus point of view, there is no antiderivative, and the fundamental theorem just doesn't work. It's kind of a loser. It's unfortunate. But if you do a real clever move, you can use polar coordinates, believe it or not, to compute the value of this integral. And again, I wish I had time, but it's a lovely little calculation that goes back surprisingly far back, a couple hundred years. Okay. All right. So I'm going to move on now to cylindrical coordinates, and cylindrical coordinates shockingly similar to polar coordinates. Let me just remind you, here was our sort of stretching factor calculation for polar. Here it is for cylindrical, and big surprise, the r and theta in polar and in cylindrical are kind of the same thing, right? With the same equations. And the only difference is that, we're keeping track of a z coordinate as well, in which z is just z. So cylindrical coordinates is so much like polar coordinates, and very little is different. The main differences are that, it's three-dimensional instead of two-dimensional. Oh, and of course, notice as well, same stretching factor. So really, really similar. So I'm going to only do one example here in cylindrical coordinates. I will start by pointing out, though, that again, you don't have to really draw the pullback. Again, you can just see what the slices look like in the XYZ space, right? So for example, perpendicular to the theta axis, here's what theta slices look like. Well, constant values of theta, I can draw that in XYZ space. Here's what a constant value of theta looks like. It's what I call a half plane, as I like to say, hinged on the z-axis, as we've discussed before. So, no big deal. You just get various different half planes hinged on the z-axis. So if you know what the slices look like in XYZ space, you don't have to pull back to r theta z space. Okay. Same sort of tips and tricks from polar. R and theta. Keep r and theta in the same order as with polar. Always put the dr inside of the d theta, which then really only gives you two options for where to put the dz, either to the outside of that pair or to the inside of that pair. That's your options. So even though technically there's six, these are the only two you should ever use. And the choice that you're going to make on this is going to be controlled by whether z, let me do it like this. If z is naturally, conveniently viewed as a function of r and theta, then you'd want to put dz on the outside, on the inside. On the other hand, if r is viewed more conveniently as a function of z, then you want to put the dr d theta on the inside. So let the algebra kind of decide for you which way you want to go on that. Okay. All right, and again, always include your stretching factor as you write down your differentials. This something you had to write down anyway. This will help you avoid the costly and surprisingly easy mistake of accidentally forgetting. Right? So again, please, I urge you to do that. And then again, same process. We identify key points, write down equations, etc. All right, let's see it in practice. So here is an example. We've got this, what we call upper half ball of radius A. So it's this solid region there. It's going to be our domain for a triple integral. How would we rewrite this in cylindrical coordinates? Well, now, just to get the ball rolling, I'm going to do dr d theta on the outside. You could do this either way. Oh, by the way, let's think about the equation for the sphere here. Here's the equation for the sphere. Just real quick. In that equation, do I prefer to view r as a function of z or z as a function of r? And the answer in this case is I don't really care much one way or the other. They're kind of, I could solve for either one sort of equally conveniently, equally inconveniently, whatever you want to call it. So do this in either order you like. Arbitrarily, I'm going to do this with r theta on the outside. In the usual order and together, as previously noted. Okay, so theta bounds. What's our range of values of theta? Well, here's a theta slice. Right, half plane hinged on the z-axis. This is what that cross section actually looks like then. Oh, come on. Right, our actual cross section is a quarter disc. Notice that this goes all the way around, so theta goes from 0 to 2 pi. Reasonable? All right, so now we fix a value of theta. So theta now fixed. So all of our attention now is going to be on this theta slice. For that theta slice, that fixed value of theta, let's now ask the next question. What's the range of values of r? Okay. You got to visualize now what does an r slice of a theta slice look like. Now an r slice itself, of course, would be a cylinder. Right? This is what it looks like when you set a constant value of r, aka an r slice. So how does that r slice intersect the theta slice? And again, geometric appeal, the way this cylinder intersects that plane is it intersects by way of just this cross section here. Just sort of a vertical slice of the theta slice. Is everybody with me? Okay. All right, so what's the deal with these slices? Well, the first one is there, where r is 0. The last one, as you continue to slice, the last one's going to be here at kind of that little point. Now I got to think of the geometry of this circumstance. What about this geometry allows me to decide what the value of r is there? Keep in mind I'm interested in the value of r. Notice that r, being the radius of this ball, coincidentally is also telling me what the value, I think I said that wrong. A, being the radius of the ball, also happens to be a value of r for this point that I'm interested in. So that means that at this point, r is a. Pretty good? Okay, and now we fix. We continue to keep theta fixed. We further now fix a value of r. So here is this, what I have in blue here. This is our r slice of our theta slice. And on that, we now need to know what's the value of z at the starting point. Okay, well that's clearly z equals 0. It's right there in the picture. God, don't you love having a picture? I mean, the picture is doing all the heavy lifting for us, right? Just if you have a good picture, as you visualize what's going on with these slices, you represent that, and then the picture tells you at least what algebra to look at in order to decide. Sometimes the picture just straight up tells you, hey, check it out, z is 0 at that point because we're in the xy plane. So the picture is just critical. It's highly, highly important. Make sure to give yourself a good picture. Okay. All right. So lower bound is 0. The upper bound, now this one we have to do some work. There's the point representing the upper bound for z. What does the picture tell us? Picture tells us that that point is on this sphere. The sphere has this cylindrical equation. And again, don't move too fast. We have to remind ourselves what we're looking for is a value of z. So I need in this equation to solve for z. That is my upper bound for z. Everybody comfortable with that part? Okay. Good deal. Okay, so things are a little bit different if you slice in the other order, and I'm not going to go through all the details on this because this is, it's the same example. I just want to focus on the interesting part. So again, I'm putting dr d theta on the inside instead of the outside, and so it's going to, okay, real quickly I'll point out z goes from 0 up to the top, which of course is A. Again, the geometry of the picture. Then on a particular z slice, some z slice here, kind of cutting through the disk. Let's ask now, what's the range of values of theta? Well, theta is going to go all the way around. So 0 to 2 pi. And then, now here's the interesting part. On a theta slice of our z slice, check out this ending point again. That ending point, again, on the sphere. Again, the sphere. Again, same equation. The big difference in this case is that you got to keep in mind now we're not looking for a z bound. Now we're looking for an r bound. And so in this equation here, we solve for r. And so this different expression is our upper r bound because of the different ordering of the slicings. Everybody follow that? Notice how I'm being very methodical as I do this. Right? You got to follow this methodical procedure. Okay. All right. Okay, proceeding along. How about spherical coordinates? Shockingly similar. You can use your coordinate conversion formulas to change the variable's function. We've already converted our stretching factor. And again, you can see what the slices look like in XYZ space. You just have to kind of think it through. Constant values of theta. We already know that. Constant values of theta are like that. This is what a theta slice looks like, therefore. Okay, constant values of phi. All right, well, that's a little weird, but how am I going to represent constant values of phi? Geometrically, if you think about it in the XYZ space, a constant value of phi is a cone. Right? Keep in mind, phi is the angle off of the z-axis. Now that's a weird kind of a slice. That takes a little bit of talent to take a knife and make slices in that sort of shape. But that's what the slice would look like. So don't think of this anymore as being flat slices, because they're just not flat slices. And then lastly, and this would be a weird one, good news, we're not going to have to deal with this particularly, but if you have constant values of rho, well, constant value of rho being distance from the origin, constant value of rho would be spheres centered at the origin. All right, so now in practice, how much of that do we really need to actually sort of be familiar with? And the good news is that it's almost always best, and again, for all practical purposes, for Math219 purposes, I don't think it's worth entertaining any alternatives. Always use this order for the differentials. d rho, d phi, d theta. It's extremely hard to come up with examples where if you just always follow this rule where you'll be led astray. It's just overwhelmingly the best choice, or at least as good as any other choice. Okay, so always go in that order. Again, don't forget your stretching factor. Again, super easy to forget because you get distracted by all the other things that are going on in the question. And again, you might as well just write it down all at once when you write down your differentials because it's always going to be there. So if you, in your your typical procedures, how your mindset of how you go about doing these questions. If you force yourself to just look anytime, I'm never going to write down these differentials by themselves. I'm always going to write down this whole thing all together. Rho squared sine phi d rho d phi d theta. Just memorize that, grouping. Always write that down all at once. Then you will minimize, at least, the likelihood of accidentally forgetting. And again, forgetting what is ultimately the big point from a multivariable calculus standpoint, right? Okay. All right, so examples. Here we go. We've got a ball, radius A, centered up here on the z-axis in such a way that this is kind of, if you will, sitting on top of the origin in the xy plane there. Right, so there's our domain. If this were the domain for a triple integral, and if I wanted to do this in spherical coordinates, let's follow the procedure here. We're going to use this order for the differentials. That means theta slicing first. Here's what a theta slice looks like. The actual cross section, like a disc, like that. And, well, how many, what ranges of values of theta? Well, these slices go all the way around. So, 0 to 2 pi. Is that cool? All right. Okay, now, you can proceed from this point in the usual way. I have just a little bit of a suggestion, and that is, instead of looking at the theta slice and the corresponding cross-section, as we have in this figure, let me criticize my figure here. This theta slice, I'm kind of looking at it from sort of an angle, right? Because theta is an angle, and I'm not looking straight at it, and that makes it a little confusing. For example, this direction there, now I know that's horizontal, but it looks below horizontal, right? That looks horizontal, right? So just there's the little optical illusions that, what should be pi over 2, visually on the picture as we see it here, looks like more than pi over 2. This can be confusing. So to avoid this issue, again, simple little hack. You don't have to do this. I just find it helpful myself. I just redraw that picture, looking at it head on. So, same picture. Right? But then what you might call, and I'm going to loosely call this the R-axis. It isn't really, but you can see why I would call that the R. That's the direction in which R is the variable that's increasing. So that R-axis that is horizontal now, furthermore, looks horizontal. So, look, suit yourself. So, you don't have to do this, but I find it helpful. Okay, that said, now what can I say about phi? What's the range of values of phi? Well, here is a phi slice. This is the phi cross section. Notice that they start straight up, where phi is 0, and they end horizontal, where phi is pi over 2. Everybody see that? Okay. All right, so we have a phi slice. Now we focus on this. We had a theta slice. Now we focus on this phi slice of our theta slice. And on that, where does rho start? Where does rho end? Well, let's see here, rho starts at, well, the point defining where it starts is the origin. That's clearly where rho is equal to 0. Right? And then the point where it ends, well, this point right here, what can I say about that point? And I have to remind myself that point is actually, let's see here, I'm going to have to zoom further out. That's actually a point kind of on the edge of the actual disk, namely that's a point that's on the sphere. So now I have another kind of a chapter 1 problem of how do I take a rectangular equation that's easy to write down, and how do I get the spherical equation? And again, chapter 1, section 1.7, I want to say, but anyway, you find it in the book. But converting from rectangular equation to spherical equation gives you that. Again, solve for rho to get our actual upper bound. Is everybody on board? Okay. Cool. Okay, now I'm going to repeat. I know I've said this before. I'm sure I'll say it again. The picture. Oh my gosh. So important. Really, really important. Don't deny yourself this huge advantage of having a decent picture to look at. It doesn't have to be, book publishable worthy. Right? It doesn't need to have that super cool computer generated shading that they do in the textbook and that kind of, you don't need that particularly, right? It just needs to be reasonably accurate. Don't be shy. Make it nice and big, right? You'd be surprised if you start with a small picture, then the more details you need to add, you find that the relevant portion ends up being so small as to be almost invisible. Right, you sort of uselessly small, so make it nice and big. Try to keep it clear. Right, if your picture starts to get messy, redraw it. Maybe hopefully improved from your previous version. Right. So I'm a big believer in having a sequence of drawings if needed. Right, you'll notice I did that here. I had this drawing and this drawing are importantly different. Right. And depending on what your thing looks like, you might have to draw multiple sort of, your first attempt to draw your solid might actually be just not good. And you might decide, okay, I feel like I learned something from this first attempt, but I need better than this. And then you draw a second version that's just an improvement of the original drawing. This is all good stuff. I'm going to point out there is technique to know. And everything that I know about drawing in math for the purpose of multivariable calculus is on those recordings that I have on my YouTube channel, Miscellaneous Topics playlist. Give them a look. I hope you'll find them useful. I think it's good stuff. If you want to find other sources on the internet for how to draw, sort of mathematical drawing, 3D figures kinds of things, go ahead. That's cool, right? But one way or the other, there is technique to know, and don't try to reinvent the wheel. And don't try also to just channel your inner Rembrandt, right? That's a mistake. That's not how good drawing is done. It's just talent exemplifying itself. No, there's things to know, and then there's chops. So you have to practice. Right? And I know that's annoying, and I know it doesn't feel like you're doing math when you're drawing, right? But it's a really important tool, very, very helpful. So I think this is very important advice right here. Okay, so here's another example. This time we have another ball, radius A, this time centered over here on the y-axis. So this changes things pretty significantly, as it turns out. So this ball, if you think about the theta slices, and here I just have to make this geometric appeal, keeping in mind that our sphere actually is kind of, if you will, tangent to the xz plane. You might say instead tangent to the x-axis. Right? It never goes over here into the sort of the far side of the x-axis. Right? So I claim that my theta slices only go from 0 to pi. You just have to see that from the geometry of the picture, right? If you like, one thing you could do if you're having trouble with this geometry, let's see here. You could try to see this, as seen from above. Imagine looking down from up there and looking down. Let's see if I have any space. Yeah, okay. I'm going to try to redraw this picture as seen from above, and it would look something like this. X-axis, Y-axis. Here's our center. Here's the ball, and then here's what our theta slices look like. Our theta slices kind of all look like that, and you can see the first one is here, and then the last one is there. That's as seen from above. This is very geometric and, okay. All right, so, theta slices. Now we focus on a theta slice, and again, it's easy to get confused, so I like to redraw that theta slice, looking at it straight on. I just find that geometrically easier myself, personal preference. You don't have to do it. And now, continuing on, let's ask the question, well, what is the slice? Right? I'm taking a slice of this disc. Geometric appeal, the slice itself is a disc. I think I said that wrong. I'm taking a slice of a ball. The slice itself is a disc. Does that make sense to everybody? By the way, if you have trouble with the geometry on this, here is an option. Buy a sack of oranges, and don't cut yourself with a knife, right? But just, be careful. But you can just make actual little slices. And just that gives you something to kind of look at, and you can see it from above. You hold the knife, you look at it, what it looks like from the side, what it looks like from above. You do the slice, you can see what that cross section looks like, right? Very helpful. And then you get to eat the oranges, so it's a win-win. So okay, there's what our cross section looks like. And now next question, what's the range of values of phi for a given value of theta? Well, this is what they look like, and they get kind of shorter as phi gets smaller, and the first one is actually going to be up there where phi is equal to 0. And as they continue on for larger values of phi, they keep getting bigger until they start getting smaller, and then they disappear at pi. So your phi range, 0 to pi. Everybody see that? And then as before, let's see here. Here's our phi slice of our theta slice. Rho starts at 0. Rho ends at this point, aka that point, aka on the sphere. And on the sphere we have that equation. By the way, now I just kind of threw that up there, right? That's the equation of the sphere. Where did that come from? Well, I took this rectangular coordinate equation and I converted in the usual chapter 1 way, right? So make sure you can do that. Make sure you can write down the rectangular equation of that sphere, and then that you can do the conversion to spherical coordinates. And of course, then we solve for rho to get our upper rho bound. All right. Okay, last example. This is mostly a drawing example, kind of a geometric visualization trick that I think is really nice. So let's start off with, you see we have a ball. That's this ball right here. But I apparently am looking to find, points that whose distance from the origin is greater than or equal to 1. So I'm looking outside of this green ball. Right? So inside of the orange, outside of the green. Everybody see that from the given algebra? So altogether then, that means that our actual set here, let's see, I'll do this in blue, our actual set is this weird shape like that. It's kind of hard to draw. I mean, look, let me criticize my drawing. This drawing makes it look like there's kind of a vertex there. There's not. There's no vertex there. What I've got here is imagine imagine that, have you ever done like melon balling? Right? So if you've got a nice round melon ball, but then you take your melon baller and you take a kind of a scoop out of the bottom of it, it won't have corners. It'll have like a rim along the bottom there, not corners. Right? So my drawing's bad. And I don't know how to make it better without also making it worse. Right? It's a hard thing to draw. And therefore, it's hard to imagine what it looks like when I take a slice of it. If I can't draw the solid exactly, how do I... this is a problem. Okay, so I just want to point out, I think this is a really good idea. Well, for one thing, you can notice that theta is going to go all the way around. This solid clearly sort of envelops part of the z-axis, so therefore it goes all the way around. Right? Okay. But okay, from there then, if I want to take this cross section of my solid, I'm going to use this clever observation here. And that is, if you're taking a cross-section of an intersection, you can instead look at the intersection of the individual cross-sections. So let's talk about this. What are the individual cross-sections? So for example, if I look at just this initial ball here, the whole ball, how do I intersect that whole ball? With this theta slice. Well, that's easy. That's a half disc. Right? That's a ball is an easy thing to understand, and slicing it, it's just going to give me this half disc. And let me go down here to draw that. That gives me. Let me do better than that. It gives me this half disc there. And then likewise, let's see here. Let's look down at this orange. Elbow. Try that again. Orange. What is the intersection of the orange ball with this theta slice? Well, again, another half disc. Nothing to it. And so now I've got a kind of a picture here, if you will. This is my theta slice. And I can see what the green part turns into, and I can see what the orange part turns into. And just recall that what I'm interested in is the part that's inside the green and outside the orange. And so, hey, no problem. There's my picture. That's what it looks like right there. Everybody have it? I just think this is a nice little geometric observation. It spares you having to visualize this fairly difficult geometric solid, and then, in your mind understanding what that thing looks like and then trying to imagine slicing it, that can be confusing. If you just take the slices of the components first, it makes the geometry quite a bit easier. Okay. All right. Details to read through. Make sure you're comfortable with that. If you have any questions, office hours, of course. Mostly this example is for the purpose of talking about that drawing issue. Okay. All right. So, there's some additional material that I think needs to be included in the course that the book glosses over far too tersely, in my opinion. And that is symmetry theorems. I think these are huge. I will expand more on why I think they're huge in a few minutes. I include them in this section on change of variables for a good reason. It turns out ultimately the theorems that I'm going to be showing you are most easily proved with change of variables, as it turns out. So this is the place to include this in the course. Which is weird, of course, because the section's already twice as big as it ought to be, right? This is generic change of variables and coordinate system integrals all into one section, and now I'm adding even more stuff. So I know this is a lot for a single section of the book, but so be it. Okay, so I'm going to start by reminding you of a theorem that you've already seen. I hope that this setup is familiar. We have this idea of an odd function motivated by the fact that odd powers of x have this property. All right, and what we mean by a symmetric interval, and I mean the way you see a symmetric interval on the x-axis, if that's the origin, a symmetric interval is an interval where these lower bounds, the lower bound and the upper bound, are negatives of each other. And another way to say that is that whenever you have a point in the interval, the negative of that point must also be in the interval. So these are equivalent formulations. Everybody willing to buy that? Okay. So given all of that, here's the big theorem. Again, I hope you've seen this before. If not, it's a pretty awesome theorem to add to your toolbox. If you have an integral where the integrand is odd and the domain is symmetric, we're done here. That integral is 0. Drop the pen, walk away. It's as easy as that. This is an awesome theorem. We just evaluated an integral without computing any antiderivatives. Antiderivatives are annoying. Big win to be able to compute an integral without having to deal with antiderivatives. Okay, awesome theorem, gotta love it. You can take a couple of different points of view on this. There is what I'm going to call the Riemann sum point of view, where you look at the terms that you're adding up and you just sort of recognize, look, because of the assumptions in play, this term in the summation and this term in the summation, they cancel each other, right? Because of the given symmetries. And all the terms cancel, and so you're left with nothing. And that's a fine point of view. We could also prove this with a substitution, aka a change of variables. And this is where I'm going to tough choices and all. We're behind schedule, and in the spirit of we need to focus on proofs, I'm not going to go through this proof, but I just want to make the case, and y'all can read it to the extent that your curiosity requires, right? But this step right here is a pullback. This is a change of variables, literally a change of variables. And so ultimately that's the thing that makes it all work is change of variables. So anyway, I just want to talk about a two-dimensional version of this same thing. And in order to be able to do the same thing in 2 dimensions, I need to be able to talk about what is odd symmetry and what does it mean for a domain to be symmetric, right? We just need sort of two-dimensional versions of these ideas that we've already used in single variable. In order to do that, I have to define something called a reflection. So, given a line, a reflection is a function that does this. It's exactly what you would think, right? Now, how you write that down, I mean, you could say that, okay, well, you move from your starting point X, perpendicularly toward the line and then continue past the line by the same distance, blah, blah, blah. Different ways that you could say it. But I think you get the idea, right? When you look at yourself in the mirror, this is what we're talking about. If you're at X, R of X is where your reflection is. Okay. All right. Okay, so with that idea of a reflection defined, an odd function is a function where when you reflect the input, you get a minus sign on the output. And I claim that this is a two-dimensional kind of version of the exact same notion of odd symmetry that we talked about in single variable. Does that seem reasonable to y'all? Okay. What does it mean for a domain to be symmetric? Well, again, it means exactly what you think it means, and how we write that down is, kind of take your pick. I like this little simple formulation that if you have a point in the region, then the reflection must also be in the region. But think Rorschach test, where you ink blot, and they fold the paper, right? It's exactly what you think. Okay. Do notice that both of these kinds of symmetries refer to a line. Right? You have to indicate what line are you talking. You can't just say a function has odd symmetry anymore. Odd symmetry over what line? What's the reflection that you're plugging in to give that odd symmetry, right? So you have to specify the line. Okay. All right, so with this setup all made, here's our theorem. I deliberately wrote this to be, in fact, I may have even literally done a copy-paste. I don't remember for sure. But this is deliberately laid out to look exactly like the one-dimensional version. And here it is. If your integrand is odd, and if your domain is symmetric, we're done here. Your integral is 0. Drop the pen, walk away. Awesome theorem, right? I don't have to, am I going to do this in polar coordinates, or am I going to have to slice the slices and then do anti-partials, and some of these anti-partials could get ugly and all of that. No. What are the bounds for my integrals? No, just boop, 0, done. That make sense? Okay. Now, a couple of warnings. Got to be careful about. You do have to make sure that both of these conditions apply. I make a big deal out of this warning because I've seen so many students. Oh my gosh, it's tragic. Who see for example, a symmetric domain, and they see daylight at the end of the tunnel, and they get a little too excited, and they forget to check if the function's odd. And if the function's not odd, then you got nothing. Right? So you do have to make sure that both of the conditions apply. It's not good enough to have just one of them. Furthermore, and again, another dangerous scenario, it's got to be the same line for both of these conditions. You can't have odd symmetry over one line and then a symmetric domain over a different line. It's not, the argument just doesn't work. Right? So, no. Okay. And again, I'm going to skip the proofs. I mean, there is this is why this is in the section on change of variables, because this is a pullback right here. And again, you can check that if you're interested and think it through. Come to office hours. I'll be happy to talk you through it. But we're not going to spend time on this proof, given the nature of the course. And then here's the Riemann sum point of view, which might actually be a little bit more satisfying. The idea is that if you have a line, and if you have a symmetric domain, well, by virtue of it being a symmetric domain, we know that in some sense every term in the Riemann sum has a buddy term in the Riemann sum, and furthermore that these are negatives and that therefore they cancel. Right? So a little bit more perhaps immediately intuitive from this Riemann sum point of view. Okay. All right, let's get our hands dirty and do one. Here we go. Here is an example. Let's compute this integral right here. Now, the very first thing I'm going to point out about this example, notice, nowhere in this example does it say use a symmetry argument to compute this integral, right? It just says compute the integral. And how you compute this integral, well, hey, you're the one with the toolbox. You decide, right? So I want to point out part of your job as a multivariable calculus student, and then once you get out of this class as a multivariable calculus practitioner, is to always be on the lookout for opportunities where you can use symmetry. You have to be heads up about this. They will not announce themselves as such, right? And so I likewise don't announce them as such in this course either. Typically, sometimes I might, but usually I won't. Okay, well, here we go. How am I going to deal with this integral? Let's draw a picture of our domain. Oh gosh, let's see. Region bounded by these two curves. Yikes. Okay, well, first let's draw this. Oh, I'll do it in blue. This curve right here, x squared minus x to the fourth. And think back to single variable calculus, curve plotting and all that. I'm going to make an appeal that it looks something kind of like this. Let's see how good I am at being consistent. All right, that's pretty good. That's a single variable calculus exercise. Again, make sure that you're good to go with inferring this picture, right? Okay, enough said. And now let's look at this other curve, y equals -1. Okay, well that's something like this. Now, I'm just going to make a geometric appeal here. You look at the formula there for that equation, the x squared and the x to the fourth. This blue curve is even, right? So it's symmetric across the y-axis. Let me draw the y-axis like that. Reflecting over the y-axis, blue curve is the same. Now, if you don't believe that, notice here's the formula for how you reflect across the y-axis. A reflection across the y-axis will leave the y-coordinate unchanged. So if that's x, then this is r of x. Notice that the y-coordinate does not change. The x-coordinate just becomes the negative of what it had been. So thus that formula. Is everybody okay with that reflection formula? Everybody's good. So you can take this reflection formula and literally plug it into there and notice that the equation works equally before or after you reflect. So there's sort of an algebraic confirmation that this is indeed a symmetric blue curve. And of course the orange curve is obviously symmetric, and so therefore I conclude that our domain, the region bounded by those two curves, this yellow region here, that yellow region is symmetric. Everybody buy it? Okay. All right. So now with that said, I claim that our integrand has odd symmetry. Now, is that obvious? Oh, no. No. Right? This is not an at-a-glance kind of a thing. In order to confirm that this function actually is odd, we've got to go back to the definition of what odd symmetry means. I'm going to have to take my reflection and plug it into F. Crank out and confirm that I actually do get this minus sign. Right? So you're going to literally plug in the reflection, do the necessary algebra, confirm you get a minus sign. Is that okay? Yeah. All right, so let's see that in action here. And this could be a little confusing. I'm going to take this reflection and plug it into there. That means, notice in particular, that means that it's negative x. That's going to go where the x is. Yeah? So having done that, plugging in the negative x, again, you know where the x was. Now I've got this expression here, and I've just got to fiddle around with this expression, do the appropriate algebra, and don't forget, well, when you cube a -1, you get a minus. Notice that when you square that minus, that goes away. And notice that this minus right here, you're taking sine of a minus, now you got to think back to trig class, right? And remember that sine is itself an odd function. And so that minus sign comes out and cancels with this minus sign to result in a plus right there. Everybody happy? And sure enough, very conveniently, we get exactly the negative of the original value of the function. So there's significant algebra to be done there to confirm that a function is odd. Is everybody on board? All right. Okay. So we're done. Game over. We win. Now let's see here. Let me confirm what we did here. Here are the 5 elements that I think are essential for having what I'm going to call a complete symmetry argument. Again, now big reminder, remember we're not interested in answers in this class, we're interested in reasoning. We're interested in arguments, right? Ideas, right? So you can't just say, oh, this integral is equal to 0, and the fact that you're correct, that just doesn't do it, right? We need to see the reasoning. So the reasoning, well, for one thing, you've got to tell me what the line of symmetry is. And notice that I've got that right here in my argument. That's the line of symmetry, is the y-axis. Notice I've got the formula for my reflection right there. Right? I need to know that the function is odd. You've got to explicitly state that the function is odd. There it is, right? The oddness of the function is one of the big ticket things in the theorem, right? So you gotta say it. But more than that, you also have to demonstrate that the function is odd. You've got to actually give me. Oh, whoops! I didn't do that well. You've got to actually give me this argument here that shows that the function is odd, because it's not obvious. There's significant algebraic work to be done there. And then lastly, you also have to point out that the domain is symmetric. And I did that up here first thing. And you can what order you do these isn't really particularly important, but you do have to state that the domain is symmetric. Now, what you don't have to do, you don't have to prove that the domain is symmetric. And my rationale there is that it's usually pretty clear from the picture when a domain is symmetric. What you do have to do is be right about it, right? You can't just assert something's symmetric if it isn't. But anyway, the point is, all of this talk that I did over here where I justified why the domain is symmetric, that was just there for, in case you were having maybe a little trouble seeing it yourself. That's just to help you see it. You do not have to supply that in the argument. Yes?
You gave us like the reflection function there.
Yeah.
I mean, that's fairly easy because we know over
yep.
there we have a negative x.
Yep. Now you gotta. This is part of. If you're going to make a symmetry argument, you do have to be able to come up with the formula for the reflection. Now, I've got some more examples that you'll see coming up. But yeah, that is part of what you have to do. That's part of the work to be done. Yeah. Because you need that formula to show the function's odd. Yeah. Okay. So heads up. I am going to be looking for all 5 of these. Let me do this in a better color. I'm going to be looking for all 5 of these. If you're going to make a symmetry argument, which, by the way, I strongly encourage you to do. After all, your alternative, is to compute this integral the old-fashioned way, which would be brutal, right? I definitely don't want to do that integral. I'm not saying I couldn't do it, but I'm saying I really, really don't want to. I don't think anyone here does, right? So, when the opportunity comes up to make a symmetry argument, by all means do it. But you do have to give me a complete argument. And again, I'm looking for all 5 of these points clearly supplied. Okay. All right. Now, a warning that I have to give you, and this is just the nature of the beast. You really have to be careful when you're going to use a symmetry argument. Because if you're wrong, right? Let's suppose that you're mistaken. Let's suppose that the domain's not symmetric. well, then there is no symmetry argument. Now, you may think to yourself, well, I got 4 of the 5 parts of the symmetry argument correct. You may think to yourself, right? But if you think about what that really says, I got 4 of the 5 components of an argument that is doomed to failure. So you get 4/5 of nothing. If the argument can't work, then it's not progress toward a valid solution, right? So be double sure. Don't just kind of, whip one out, right? Just take your time, take a breath, right? Look at it very closely and make sure that the symmetry argument actually works before you use it. Okay. All right. Now let's look at this work here. Here's an example, and here is an answer supplied by a student, hypothetical student, and how would this get graded? Now the student looks and identifies and sees, ooh, I love this domain. Oh, that's a square. There's lots of symmetries there. Sweet. And this looks nice. I see some odd numbers, and I see a lot of potential for, you know what? I think this is probably just a symmetry thing. We've got a symmetric domain, odd symmetry, boom. You can see a student might be tempted to write this down. Okay, this student has done 2 of the 5 requirements. This student has noted that the domain is symmetric. The student has noted that the function has odd symmetry. The student has absolutely failed to indicate what line. What are you talking about? Symmetric over what? This domain's symmetric over 4 separate lines. Which one are you using? Right? Oh, this function's odd? Well, it's not just because it has odd numbers in it. Over what line is that function odd? Not clear, and certainly not indicated. Right? No formula for reflection, no demonstration that the function's odd. Again, there's work to be done there. Can't just go around asserting things that are really not clear. Right? So this student gets 2 out of 5, which typically on a question would mean about 40% of the points. Right? So it's just a warning, right? Make sure to give me all 5 of the steps, all 5 of the required parts of the argument, and just give yourself a little checklist and make sure you give me all. Okay. Here's another example. So, I've got some curves here. Here's what our picture looks like. You want to compute this integral. Pretty unappealing looking integral, high powers, weird curves, corners everywhere, right? Pretty unappealing looking task. But then you notice there's a symmetry across that line. Just looking at the domain. Now, again, you don't have to prove that domain is symmetric, but I just, appeal to look at the nature of the lines, and I think that's a pretty easy pitch, that domain's symmetric. Does everybody see that? Is everybody comfortable with that? Okay, so we've got a line down. Now, what's the formula for the reflection? Here's a trick for how to, in this case, identify what happens when you reflect the point XY. When you reflect like that, notice that what I'm going to call this little rectangular frame that I have in green there, that rectangular frame will reflect like that. So it's just easier to kind of see sometimes what's happening to straight horizontal and straight vertical edges as opposed to some randomly angled thing. It's kind of hard to tell where the blue point actually is, but the green horizontal and the green vertical, it's easy to see what happens to those. And as a result, you can read off what the reflection is. The reflection is, let's see here, I'll use dark blue, this point right there. Negative y, comma, negative x. Now that's just a peel from the picture. I think it's a nice trick for identifying a reflection formula. In some cases, so if you're reflecting over a 45-degree line, this is a nice trick, right? If you're reflecting over an axis, it's usually just a pretty easy observation of one of the coordinates is going to get a minus sign and the other one's not going to change. And then I suppose, by the way, there could be some trickier cases where maybe you're reflecting over a differently angled line, and there you can use linear algebra and some nice tricks that you can play with linear algebra. Again, think about the fact that every reflection is a linear correction. Every reflection over the origin, a line containing the origin, it's a linear transformation. That means we've got a matrix. That means I can study the columns. Those are the images of the standard basis vectors. And you can do like that. That makes sense to everybody? Okay, so now how do I know that the function is odd? Well, okay, as usual, I'm going to have to take my formula for my reflection, plug it into F, be real careful with your minus signs, right? And, do the necessary algebra, but the nice punchline is that indeed, as requested and required, you do get exactly the negative of the original value of the function, and boom, score, we win. All right. Okay, let's see here. Real quick, I just want to point out that the symmetry does not always work. Sometimes it is, there's landmines out there. And again, this is not me being a jerk by creating landmines for y'all to step on, right? The world is the jerk. The world creates these landmines. And so notice this easy example here. I've got a domain where the vertices are, 0, 2, -1, 0, 1, 0, and you see that. And then you think, oh, well, look, check it out. That's symmetric. And my integrand is clearly odd. Boom! Symmetry. Walk away. Right? A lot of students would say symmetry and go here. And this is absolutely wrong. 100% wrong. Subtly. Because the domain is symmetric only over the y-axis. Right? But if you look at this integrand here, this integrand is odd only over the x-axis. Only if you're reflecting on that line, which turns y into minus y. So there is no symmetry argument here. This is the landmine to be watching out for. Right? And so, again, any argument that you make about this integral that's in the direction of symmetry is worth nothing, because there is no symmetry argument to be made. So, very, very careful. And we're out of time, and I'm sorry I went over. We will call it a day here. We'll pick up here next time. And, see y'all later. Real quick. Believe it or not, today, being Thursday, is the last day of fair game material for exam 2. Coming up real fast. What is it? On Monday, I think it is. So, anyway, just thought I'd remind y'all of that. Okay, see you later.